Okay, shall we? Yes, got. Microphone is here. Eleonora, you are there? Yeah.
Hi, yeah. Good morning.
Can you please start your presentation? Just
Yeah.
put the first slide, maybe, just to check up.
Arvind, can you speak once?
Can you see it?
Yes.
Yeah. Okay, sure. So we can get started. I guess we are kind of in a mood, right? So, okay. First of all, I would like to welcome all of you for this talk for lab visits, and we have with us Dr. Eleonora Perego. And a little bit of introduction about her. And she studies physics at University of Milano, Italy, and then 2020 she obtained a PhD in biophysics, working in the group of Dr. Sarah Koester, that's in Germany. And she studied protein-protein interactions, which combined fluorescence spectroscopy and microfluidic devices. And since 2021, she's working at Italian Institute of Technology, Genoa, in the molecular microscopy and spectroscopy research in the lab of Dr. Giuseppe Biccidomini. Her interests include applications in fluorescence spectroscopy, such as fluorescence fluctuation spectroscopy and fluorescence lifetime imaging. And she's asking very interesting questions and trying to solve these questions using the technique that she has developed. And these questions range from neuroscience to RNA biology. It's a very, very interesting work that she's carrying out at the Italian Institute of Technology. And we're going to see some of the new research and new kind of work that is actually made possible by the techniques that she has developed. So Eleonora, please take over. Please go ahead and deliver.
Thank you for the introduction. Thank you so much. And yeah, good morning, everyone. I'm Eleonora. And today I will show you basically how we can increase the information and use the information we get from single photons that we can acquire by a novel detector that was developed really recently from my lab. So, and this new detector, in combination with a special time tagging module, allow us to basically really get to the single photon. And we want to use this method to study biomolecular condensates. And I will go into more detail later. And if you have any question, also feel free to basically stop me anytime. So this is my group in IIT. Here on the back, you see basically the building where we work. And you might have already seen some people of this group because they presented last year or like recent here. And in particular, Giuseppe, so my supervisor, presented here, but also Dr. Elise Landers presented, and they were both more focusing on the application, I guess. Especially Eli was showing you how to use, again, the same detector and the same combination of methods to basically get to the single molecule level of imaging. What we do, we are basically a microscopy lab, and we develop new methods, and we are mostly focused on confocal laser scanning microscope. What is a confocal laser scanning microscope? It's a confocal microscope. This is, you see here by the pinhole with a photodiode, which is equipped with a laser. The laser is focused on the sample, and the laser is scanning the sample. So what we typically do is we have an object and the laser scanning the sample. The data are acquired by a single element detector, and we can form an image, which is diffraction limited. Our new detector, because of the single element detector, we have a loss of information, because basically we are integrating over time and all integrating in time and space. We are integrating all over the element detector, the area of the detector. So we, because of this integration, and typically also temporarily we are binning in long bins, we are losing some information. What was developed in my lab is so-called SPAD array detector, which is basically a small camera with infinite frame rate. How it works is that in this case, it's composed by 5 by 5 single photon element avalanche detector. So we have basically, instead of having only one detector, we have 25 here. And what we can do is basically directly image the diffraction, the detection volume. We don't need a pinhole, a physical pinhole anymore into the setup, because every single element will act as a pinhole. So now, instead of having basically one single element, what we do is having, you see here, an array of detector elements, and we are basically imaging the image plane. And so instead of having basically only one image from the object that we are scanning, we have 25. So we have more information now on our sample. We have a 4D data set where you can see it has the position X and Y of the scanning and the position where each single photon are hitting on the detector. And we can see it basically as a 5 by 5 scan images. And basically what we have is a 5 by 5 also point spread function. So the response of, the description basically of the detector volume, it's also reflected into our detector. So we have basically 25 images that are all the same but all slightly different. And this difference comes from the differences in the point spread function. What we are doing is basically seeing the sample from different slightly different angle of perspective. So what we can do is actually use this extra information in a method that's called image scanning microscopy that allow us to increase the resolution we can achieve. So we take all the information we get to all these slightly different angles, and we basically shift them back into the center and sum all the images to get a super resolved image. And you'll see some of these images later. So we have an element here. You see the SPAD array detector inside a setup. You see that we have basically here, these are all the cables getting all the data from the single channels. And in this case, it's a version that has a cooled sensor, which allows to decrease even further the background signal. And it's specifically designed for laser scanning microscopy. Here you see it in a zoom version. Basically, in this case, it's 5 by 5, but there's now also a commercial version of the SPAD array detector that's 7 by 7. And it's an array of small single photon avalanche diode. It's small enough that it's not a camera, and it's 25 channel or 49 are still are quiet, but the data stream that we have is still quite handy, and we can analyze them to very detail. But it's big enough that we can directly image the confocal volume. So we have basically, instead of averaging out the signal, we have now a sub-diffracted spatial information of where the photon hits the detector and where the photons were coming from our volume. And we can also reach really impressive temporal velocity, temporal information about 100 picoseconds. How do we reach these values? Well, as you've seen before, we have a lot of cables, and they are basically connected to a special card, which was developed also in my lab. It's an open source project, as actually all the projects we are doing. You can find all of our project in the GitHub page of our lab. And this card was specifically built for a SPAD array detector, and it's able to temporally and spatially tag each single photon that arrives with very high precision, both in space and time. It's a custom build. You see it's built on FPGA that's commercially available. There are some few other connectors, either to connect, in this case, these two that are interchangeable are used to connect the SPAD array detector, and this one is actually the USB connector to the computer to stream the data. And how it works, basically, it works as a slave inside our microscope, and it can be implemented in any other microscope also. In our case, we have two lasers. They are they are focused together in a fiber. They are entering the galvo mirrors, they're entering the objective and going to the sample. The sample holder, we have a temperature control stage so that we can also perform, for example, measurement in live samples. Then the fluorescence is emitted, it goes back, it travels back, and then we can divide the signal into SPAD array detector or also into more conventional detectors. And this, all the data coming from the detector enter into our TTM card or time tag card, which we call bright eyes. And the idea is that this card acts as a slave. It just collects what is detected by the detectors, and it has it's fed with several sync signals, so we can basically measure precisely the arrival time of each single photon depending on the sync signal of the laser. This works by using pulse laser, and we are able to measure the start-stop time, so the arrival time of each single photon, and we can also relate it to several other reference channels, signals, such as like the line or when pixel was switched. So we have fully control of time and space of each single photon. We are increasing again the space-time data set, because this time, instead of having only the position on that we are scanning and the position on the detector, we have also the absolute time. So, for example, when the frame is over or when we switch the pixel, but we also have this delta t time, which is the arrival time of each single photon. So we have space and time information at really a single photon level. So what can we do with it? I'm focusing mostly in application. So we decided to also apply basically the methods that we are developing to biological problems. And today I will show you, for example, a few examples that we worked on by combining this card, this bright eye CTM, with our new SPAD array detector. And it's quite interesting, this combination, because actually it allows us to access time scales and space scale that were quite restricted before. With conventional microscopy, it's typically either you do maybe imaging or spectroscopy, but it's rare to find a method, let's say, that can do both. While here we can look at our data, because we have our data to such a single because it's a single photon level, we can really access different space time. So we can access the nanosecond time domain, so accessing, for example, photophysical properties of the sample, but also longer time scale by binning the data that we get, accessing the dynamics, for example, of the sample we are measuring, but also to access larger dynamics such like cells movement. And this space is similar. We can really look at cellular compartments like organelles, or having information from a sub-diffraction area, like to a nanometer level, but also going larger. And this allows us to be very, very, let's say, comfortable in what we can study and what we can do and what we can achieve. And the example I want to bring you today of what we study is studying the formation of biomolecular condensate. What are these condensates? They are recently being discovered in cells. Basically, cells can organize proteins and molecules in condensate that don't have a membrane. So they are called, it's called liquid-liquid to phase separation, this process, and we have a sort of demixing of the molecules that were previously like just diffusing inside the cells, organized in some sort of condensate inside, which don't have any membrane. And cells use this liquid-liquid condensate to organize in space and time certain processes. For example, the one that we will focus today is the oxidative stress. When a cell goes under oxidative stress, what it does is create these membraneless organelles that in this case are called stress granules. And they are composed by RNAs and proteins that are fundamental for the cells. So the cell is kind of sequestering these molecules in order to survive the stress phase. And then once the stress is gone, she's releasing them back into the cytoplasm. And they are called liquid condensate because they act as liquids. They are round, they form droplets, there can be mixing, and inside molecules are moving quite freely, and not quite freely, but they are moving inside the condensate, and there can be also exchange with the outside. However, sometimes when there are, for example, some mutation, this liquid and membraneless organelles can go into aberrant phase and transform into solids. And once that we have this transition liquid to solid, then we are looking to some troubles. In fact, in most of the cases, these solid aggregates and are actually toxic to cells, and they are found in relation with a lot of neurodegenerative diseases. For example, in the case of stress granules that we will discuss, these are found in relation with ALS diseases. So we have the liquid-like condensates, which don't have membranes. There can be exchange in molecules, and most importantly, they are reversible, so they can be dissolved. But we have also aberrant condensates that are solid-like. Also, they don't have membranes as boundary, but there is no exchange of molecules, and there are no, they are not reversible, so they become toxic to cells. What is inside this condensate? Typically, it's proteins and RNAs. They are governed by weak multivalent interaction like van der Waals. And typically, the proteins that are found inside this condensate are RNA binding proteins that have some sort of intrinsically disordered domain. So we can find either RNA-RNA interacting molecules, but also protein-protein or RNA-proteins aggregates. And the questions are still here because they are still recent, sort of recent discovery, and people are finding them happening at various stages of cells. A lot is still unknown. And so we don't know how these granules forms, what is the liquid to liquid transition, but also how that we can go from liquid to solid, to liquid to solid. So this transition is still don't know. What are the dynamics inside these condensates? And if there's, for example, a change of the protein or the condensate environment where they are, and if there are actually some interaction, like some strong interaction between the proteins involved. And can we quantify this process? It's quite difficult because this is a process that goes from basically single proteins in the cytoplasm to actually organized, and they can take various spatial and time range. And of course we can, and I will show you how we can use basically our setup to do it. And with basically one single or almost a single data set, we can access all of this information in once. So we will start with how to access the macro environment, or like the cellular environment in this condensate. And how we can do it is perform the super resolution microscopy I introduced you before. It's called image scanning microscope, where we basically employ the spatial information we get from the SPAD array detector to reconstruct and to reconstruct images in a super resolved way. We can take images over time, and access basically the changes on a cellular level. And this is a technique that my lab is really strong in. We have also recently released packages on Pari, where you can reconstruct as an open source, reconstruct these images. And this is the cellular model we are going to study. Here you see SK and B cells that are expressed in two proteins. One is G3BP1. It's fused with GFP, so you see it in this case, you see it in channel. And it's a protein that's in the cytoplasm, and it's uniformly expressed. And it's a marker of oxidative stress. So we are going to study how the oxidative stress is changing the dynamics of this protein. The second protein, it's called FAS. In this case, is tagged with RFP. You see it here in magenta. You see it in the nuclei. And this is actually the protein. It's an RNA binding protein, and it is related to ALS. When it's in fact, here you see it in the nuclei. There are some mutation of the protein that can move this protein from the nuclei to the cytoplasm. When we go under oxidative stress, what happens? Basically, we have the formation of these condensates, this liquid-liquid condensate, which are called stress granules. And you see them here in the cytoplasm. And because the oxidative stress is acting mainly on the cytoplasm, the stress granules are actually found only in the cytoplasm, so you don't see anything happening in the protein that's restricted to the nuclei. However, as I told you, when we have a mutation, here we have a mutation in position 525, we see that also FAS is located in the cytoplasm, which imply we have basically two defect in these cells. First, we have a loss of function in the nuclei because FAS cannot operate as normally. So it's an RNA binding protein. What it does typically is shuttle RNAs in and out from the nuclei. Plus, we have a gain of defects in the cytoplasm because under oxidative stress, also FAS is forming granules. And sometimes these FAS granules are by themselves in the sense that there's no G3BP, but most of the times FAS granules are recruited inside the stress granules together with G3BP. And with the imaging only, we can see basically what's happening on the larger time scale and on the larger space scale. But we don't know if there's some changing inside the granules, how these proteins are moving. And for that, we decided to access also, let's say, the millisecond time domain, measuring the dynamics directly of these proteins and the microenvironment of these proteins, performing a method that's called spot variation FCS. So maybe some of you know how FCS works, but I want to give a quick recap in general. So FCS, or fluorescent correlation spectroscopy, it's a method that was developed in the 70s, and then it really gained much interest from the 90s on. What it allows to do is to basically measure the dynamics, the properties of a single particle moving in your sample by measuring the intensity fluctuation in one point. So let's say we have molecules in the sample. This is our confocal volume. You can also perform this method using, for example, 2-photon excitation or stud microscopy. You just need to have a very defined volume. And then you have the molecules that are moving. And this movement in and out of volume, it's basically creating intensity fluctuations over time. So now what can we do with this intensity fluctuation? We can, for example, correlate in time a different lag time, the intensity signal. And this gives us a measurement of how long each single molecule was inside the detection volume. So how long it took for a molecule moving to cross the detection volume. And this gives us information about the dynamics and about the size in an indirect way and on the concentration. So typically, this is how it looks, this autocorrelation function. So the correlation, because it's done with itself, it's called autocorrelation. When we have a fast molecule, it will decay much at shorter time scale. When we have slow molecule, a bigger molecule, it will decay at lower time scale. And this is used to study aggregation processes, particles measurement, for example, even in flow cytology, and interaction processes. So we can measure the diffusion, the so-called diffusion, or sort of velocity, the diffusion coefficient, because for smaller diffusion coefficient, slower molecule, we will have the autocorrelation curve shifting on the right. It is also dependent on the concentration of molecule in the sample. It's inversely proportional to the concentration, the amplitude, as you can see here. And we are also able to distinguish multiple components inside, because we will see either one decay or multiple decay in the autocorrelation function. So this was the conventional, let's say, FCS. But here we have a new detector that gives us basically, instead of only one intensity time trace, 25 intensity time trace, because of exactly the SPAD array detector. And here you see, for example, the diffusion of one fluorescent nanobit that's passing and moving inside our detection volume. So we can really image directly the detection volume. What can we do now? We can perform a method that's called spot variation. So we can go a little bit more further into our sample and get a bit more information. If we would have a normal detector, we would do a measurement here, and basically we would collect all the movement inside here. We would not be able to distinguish if this big one would be our confocal volume only. We will not be able to distinguish the movement of a single molecule moving from the big one. And we will not be able to distinguish the movement that's happening inside, for example, the condensate. So we are basically averaging out the samples information. But with the SPAD array detector, what we can do is basically focus in our sample to get really the diffusion properties at different volumes. And this method was also performed with conventional detectors, but the idea is to create these different volumes of detection. And what was done in conventional microscopy was either using STED, so pumping up the STED power to create smaller and smaller volume, or changing the back aperture in the microscope, which will change basically your detection volume. With a SPAD array detector, actually, smartly enough, we can do it without any change on the hardware of the microscope, because we can basically simply, in a post-processing phase, integrate the signal coming from different parts of our detector, because our detector is able to directly image the detection volume and then use them as the different volumes. So here we are accessing 3 volumes. With a 5x5, we can access up to 5 volumes, more or less, with different volumes. But you see here, the idea is quite simple. We can either consider only the central element and getting the signal coming only from the central element and getting a decay function, or the 3x3, we get, again, we sum all the signal coming from the 3x3, we autocorrelate it, and we have another decay function, or we consider the whole area 5x5, we integrate all the signal, and we correlate the function. This would be the autocorrelation function as if we had a single element detector. And what can we do with these three? We fit them and we get basically the three diffusion time dependent on the three volumes that we are measuring. And this can be related to a law that's called diffusion law. Basically, it tells us that if the diffusion time it's linear and goes inside the intercept is 0, dependent on the area of the detection volume, the molecules are freely diffusing, in the sense that if we zoom in and in and in, there's not going to be sort of difference in the movement that we are measuring. So the molecules are freely diffusing inside the sample. If the intercept is bigger than 0, we can infer that the molecules probably are restricted into domains. So they are restricted into domains and they are basically diffusing inside the domains, and maybe they can hop to different domains, but they have this type of movement. If the intercept is smaller than 0, then we are inferring that the molecules are probably diffusing in a very strong confined meshwork, and the movement is very restricted. We can actually really use this information to get not only the velocity of this movement, but also the type of movement that the molecules are doing. And we perform this method again into our cell samples. You see here we have cell expressing G3BP, that was the marker for oxidative stress, before the stress and after the stress. After the stress, you see we have stress granules forms. The question is, are the molecules inside the granules moving differently than before the stress? And the answer is yes. So first of all, they are moving faster here. Here you see that the diffusion, the autocorrelation curves are decaying slightly to longer time scale. And second of all, they are diffusing in two different ways, completely two different. Before the stress, the diffusion is closer, let's say, to a type of free diffusion. In this case, the intercept is smaller than 0, so we are in the meshwork domain, in the meshwork type of movement. And once the stress is applied, we are measuring inside of a stress granules, we are actually able to measure a confined type of movement, which further confirm that these are most probably liquid condensates. We can go further. We can also, instead of looking at the intercept of this curve, instead of considering the diffusion, the time decay, we can consider the diffusion coefficient, and we introduce this new parameter, which here we call confinement strength, and it's simply the ratio between the diffusion coefficient that we measure at the smallest volume we can achieve with the diffusion coefficient we measure with the bigger volume we achieve. And it basically gives us the same information as the slope of before, but this single parameter allows us to qualitatively simply look at different compare a different cell state we want. So again, we have the three type of movement, and what we did was basically measure the cells, wild type and the mutated cells, so the one where Fus is in the nucleo and Fus is in the cytoplasm in this case. And what we are plotting here is the diffusion coefficient against this parameter, the confinement strength. So we are correlating how fast, let's say, the molecule move with the type of movement that they are doing. Here you see the data for G3BP1, so the cytosolic stress response protein, and for Fus protein, before the stress and after the stress. We see that for G3BP1, before the stress, after the stress, before the stress we have a high diffusion coefficient, so they move quite fast. And after the stress, their movement is really restricted. And we see a switch from type of movement that's a free, more or less, we have free diffusion coefficient, free type of movement to a confined movement. And this the type of behavior we see it both in the wild type cells, but also in the mutated cells. So G3BP1 doesn't see too much the mutation, it seems. While for the second protein, fast protein, we do really see a difference. So in the wild type case, where we would not expect to see any type of difference before and after the stress, that's what we measure. And this is because in this case, the cell is in the nuclei compartment and it's not affected by the oxidative stress happening. So the fast protein is moving slower compared to G3BP1, and before or after the stress, there's no change. While in the mutation condition, we do see a change. And interestingly enough, this change between stress and non-stress, it's only visible with our method. In the sense that if we would perform a conventional FCS, what we would be able to measure, it's only D. It's only the diffusion coefficient. And you see that there is actually not much of a difference between before the stress and after the stress. However, if we look at how the molecules are diffusing inside the granules, we see there's quite of a difference. If before they are diffusing in a meshwork type of domain, so we have that the protein are really restricted inside the granules. Once we are under stress and the fused granules are fusing inside the stress granules, the fused protein really change the type of movement, and it's also moving inside domain. So it's integrated inside a liquid condensate. What we can do with our data with exactly the same data set is also looking further and looking at the nano environment. And to look at the nano environment of the single protein, what we do is measure the fluorescence lifetime. Again, a quick recap. Basically, with the time tagging card, we are able to measure the arrival time, time of each single photon compared to the laser pulse. And what we can do is build an histogram of the fluorescence decay. And this can be fitted typically with a single exponential function, and we retrieve the value of the fluorescence lifetime. We can do it in a single point, or we can do it for an image. If we are scanning an image for each pixel, we can create decay, an arrival time decay histogram. We can fit it, and basically we can give a value of the fluorescence lifetime for each single pixel. And this is quite interesting because it has been shown that the fluorescence lifetime can be used as a reporter for changing in the nano environment of the proteins. It's changing depending on the pH, on the viscosity, on the concentration, on the conformation of the dye. So our idea is that we can go from structural imaging and information and dynamic information to also functional information. Here you see the cells under stress. On the right, on the left, you see the intensity information, and on the right, the lifetime information. And what we can do is actually divide from the lifetime for the longer lifetime compared to the shorter lifetime. And you see here how the shorter lifetime are exactly the one inside the granules. So here I'm not showing to you, but we can use the lifetime-based segmentation, like here, to segmentate organelles inside the cells, and then perform, for example, some sort of shape analysis of the organelles we are interested in. We also confirm that the lifetime is different inside stress granules compared to outside by measuring directly in single points of the cell, the changing in lifetime, and we see that the lifetime decrease inside the granules, and actually we are able to integrate the lifetime change together with the movement change. Here you see the diffusion coefficient and the lifetime value, and we see that as the diffusion coefficient decrease, which means that we are forming the stress granules, we are forming the condensate. Also, the lifetime is decreasing. So it can really be used to sense changing the environment inside our sample. And we are able with this to link, to create a link to study basically the nano-environment together with the mobility of the protein. Last point I want to show, again, with the same data set, what we can perform is cross-correlation spectroscopy measurements, which give us information about the interaction. As I show you in the beginning, in this setup, we have two colors. What we can do is basically go to investigate the interaction of two components. So we can measure the intensity of one color, the intensity of the other color, correlate them in time within each other, having the autocorrelation function, but also cross-correlating the signal with each other. And this tells us if the cross-correlation is high, you see it here in gray, it means that the two type of molecules are moving together. If the cross-correlation is low, it means that they are moving separately. So it gives us a direct information, a direct access about the interaction. We did it again on our sample. Here you see G3BP again in cyan and fast protein in magenta. Here you see this is the mutated case, where they actually are compartmentalized both in the same, in the cytosol. You see under oxidative stress, we have the formation of this. What we did was measure both of them, both protein before and after the stress. And we can, just to remind you, for each single measurement, we can also perform lifetime measurement. These are the decay, the arrival time decay for both proteins. Simultaneously, we measure the mobility of the single proteins. Here you see autocorrelation function of G3BP and the autocorrelation function of FAS and the cross-correlation function. These two are normalized, and I hope you can appreciate how here basically the cross-correlation amplitude is much, much higher compared to the case where they are non-stressed. So we are actually able to directly measure that there is actually an interaction inside the stress granules between the two proteins. And if we compare the relative amplitudes of the cross-correlation, we see that after the stress, in this case, they are much higher compared to before the stress, which means that we confirm for the first time an interaction. To conclude, I show you basically a platform, Bright Eyes TTM, which allows, in combination of a new detector, to time tag a space tag single photon. We created basically a low-cost open source platform for single photon microscopy. It's a plug-in and play design, in the sense that I show you here how we use it to perform measurements on the laser scanning microscope we have, but you can also attach it to any other microscope, and it allows to unlock multidimensional space and time resolve measurements. And we use it to start unveiling the dynamics inside the formation of biomolecular condensate. So it's basically we are really able to start bridging structure and function to create a comprehensive imaging and spectroscopy measurements. As I told you, everything we do, it's open source. We have really an open science mission in our lab. You can find the instruction for building the Bright Eyes card that I showed you before, but also basically instruction how to build a setup and how to use the novel detector we are using, and also for the first time also microscope control software and analysis software. You can find everything on our GitHub page. And with that, I want to thank everyone in my group. We are all working hard to basically show how this detector can really revolutionize all microscopy, and thank you for the attention. Just one thing, we are looking for postdocs. If some of you is interested after or know someone, yeah, let us know. Just send us an email.
Okay, right. Thanks a lot. I mean, it was really a wonderful talk, which I think is the frontier of detector technology and mostly applied to fluorescence microscopy. So this basically goes on to show that how the frontiers of science is being pushed using new technologies, new detectors, right? Eleonora, I have some questions that I want to ask you. You are able to hear me?
Yes, yeah.
Right. So you talked about dilute and dense phases, and then you talked about molecular motions. So I was just wondering, what do you think is the time scale of this molecular motions, and if your detector is good enough to really, it has good time resolution to really look at these motions?
Actually, yes. So we can, I mean, as I show you, this detector can also access really easily the nanosecond timescale, because we can really access the single photon time arrival. We are basically really limited by almost the computer power. And in this case, inside cells, I would say that we don't have much problem to access the single molecule motion, because they are in the order of milliseconds. So this works quite well. We are also able to measure faster things as proteins in vitro, which diffuse quite faster. Motion in the order of microseconds and milliseconds we can definitely achieve easily.
Eleonora, but how fast your detectors can actually detect? Like, what is the time resolution for your detector?
So it's almost non-limited. If we are acquiring in one single point, it is each single detector. The real restriction is the dead time. So in the sense that every time that it detects a photon, it's switched off for about 50 nanoseconds to avoid to have these electron artifacts when it detects. But this is true for a single of one of the 25 detectors. So basically, it's almost unlimited, the frame rate.
Okay. So if any one of you have question, you can ask. Do you have anything that you want to ask? Come here and ask. Yeah, we have a question, Eleonora.
Yeah.
Hi, this SPED array detector that's made of some arrays of photodiodes, probably, is it? And each pixel is associated with any electronic circuit in it.
Sorry, I didn't understand probably the last part. Yeah, it's basically an array of photodiodes.
Yes.
And
other than
yeah.
this sensor, is there any electronic circuit integrated with that sensor?
So I have to admit that I don't know if there's electronic directly integrated with the sensor, because so this sensor was developed in collaboration with the Politecnico of Milan, and especially I am more on the application side. So from what I know, the most of the electronics is on the time tagging card level. But I'm not sure. I'm sorry. If you want, I can give you more. I can give you some reference where it's really described more into detail.
Right. Okay. Anyone of you want to ask anything that will pop up in your mind? So online, let us check if there is something online. I don't see any more questions, Eleonora. It was really a good talk, and I'm really happy to see that how you are able to push the boundaries of science, asking interesting questions, based on the detector that you have developed. Okay, thanks a lot for giving the
Thank
talk,
you
and
so much
it
for
was,
the
yeah,
opportunity and have a
right.
good
Thank you.
day.
Bye. Yeah. Okay. Let's thank her once more. Yeah. Sure.
Thank you.
Bye. Yeah. Thank you.